So here with the beginning of chapter 9, we're going to sort of change our focus of what we're doing right now. So we've been doing a lot regarding bonding lately, but now we're going to be talking about gases and properties as well as calculations that have to do with gases. And it turns out we have to handle gases a lot differently than other states of matter. Now, why is that? Well, the issue is that gases have a number of properties that are unique to gases. So think about some of the things that make gases behave differently from, say, solids and liquids. And what would be the first things that you would come up with? Well, one of the most obvious things might be that gases have no definite shape. Whatever container they're in, or whatever room, whatever space they're in, a gas will adopt its shape to that area. But in addition to no definite shape, they have no definite volume as well. And that really makes them different from solids and liquids. Solids and liquids, for the most part, have a definite shape for solids, and in both cases have a fairly definite volume. Those aren't really things that change. But for gases, they change very, very easily. Gases can be compressed. They have a very weak attraction to their neighbor. In other words, if you think about solids and liquids, and if you try to mix them, some combinations of solids and liquids will mix very, very easily. For example, if you add salt and water, they will mix very easily. But if you add oil and water have very different polarities. They're not attracted to each other. And so they will separate out as two completely separate layers. Well, when it comes to gases, that actually doesn't matter. In the case of gases, there's almost no attraction to neighboring molecules, and so it doesn't matter what the neighboring molecules are. In addition, because of this, mixtures of gases are almost always homogeneous. You won't really see two layers. And if you do see two layers of gases, it, in most cases, will mean they just haven't had enough time to mix thoroughly. A gas will exert pressure on its container. And finally, over 99% of a gas is actually empty space. So there's a lot of space in between the atoms or molecules. All right, when we deal with gases, we have to also talk about pressure. So how do we define pressure? How do we calculate pressure? What are the units that we use? So pressure is equal to force over area. And the units on these, force is generally measured in newtons, while area is in meters squared. And so a newton, if you're not familiar with that term, if you haven't taken physics yet, is a kilogram meter over second squared. And so this unit now, Newton per meter squared, we define as 1 Pascal. Now, pressure is something you've probably seen in other units, especially if you watch the weather. And the most common unit you may have seen for weather, where they talk about the barometric pressure, is inches, or inches of mercury. Now, that's not a unit we're going to use in here in general, because that's not an SI unit. The only issue with pascals, though, is the pascal turns out it's a very, very small unit. And so if we talk about what we'd call standard atmospheric pressure, standard atmospheric pressure is approximately 101,325 pascals. So more often we talk about kilopascals, gives us more manageable numbers to deal with. But we also often use atmospheres. And so standard atmospheric pressure is 1 atmosphere. If you're looking for the numbers to get the unit conversions from one unit to another, it's these numbers I'm giving you here. 101,325 pascals is equivalent to 1 atmosphere. Now, I did mention inches of mercury, but what we use more commonly is millimeters of mercury. But you could easily convert that to inches. You would just need a conversion between millimeters and inches. And then sometimes we also see torr, but it turns out torr and millimeters of mercury are really the same unit. So we're now going to get into gas laws. Gas laws allow us to relate pressure, volume, temperature, and the number of moles of the gas that we have. Now, in reality, the physical behavior of gases is dependent on what gas is involved. But what we're going to do is we're going to assume what we call ideal gas behavior. Now, do all gases follow ideal gas behavior? The answer is no, but in general, it gives us a close enough approximation that we can use it. Later on in this chapter, when we get to the ideal gas law, I'll show you what you can do if something deviates from the ideal gas law, but it's not something we're really going to worry about in this course. So our first 4 gas laws that we're going to look at, we'll look at these terms here, with 2 of them being constant and 2 of them changing. At the end, then, we'll combine these into 2 larger gas laws, which involve more of these. But we start with Boyle's law. Boyle's law assumes that we have constant temperature and that the number of moles of the gas do not change. So in other words, we're looking at pressure and volume. So think about the following. What happens to a gas if we change the pressure? What does that do to the volume? Or in other words, if we increase the pressure on a gas, will the volume get larger or will the volume get smaller? Well, logically, it should follow that the more we increase the pressure, the smaller the volume gets. And so we find that the pressure of a gas is inversely proportional to the volume. And so we can write Boyle's law as the pressure is equal to some constant K divided by the volume. Just one problem here. This constant K is different for every gas. So what we do instead is we're going to solve this equation for K. And we get K is equal to pressure times volume. And so now let's think of some sample of some gas. Doesn't matter what gas, but we're going to measure its pressure and volume at some point. And so we get P1 times V1 is equal to the constant K. Now we take that same sample of gas and we change the pressure, which will change its volume. So we have a new pressure, P2, at a new volume, V2. But because this is the same gas, the constant K doesn't change. And as long as we're talking about the same gas, which is what we assumed here to start, these two values of K are the same. So we can bring these together. And we can now say that P1 V1 equals P2 V2. And so now we have the form of Boyle's law that we can use much more easily. Why is that? Well, this K that was going to be problematic to deal with because we'd have to look it up every time we used a different gas, it doesn't show up in this equation. And so we can just disregard it entirely. Now, what units do we need to use for pressure and volume? Well, the answer is essentially that it doesn't matter. The only thing that matters is that we use the same units on both sides. But of all the pressure units that we just discussed on the previous page, we can use any of those pressure units. Again, we just have to use the same units on both sides. All right, so next we can look at Charles' law. Charles' law now has constant pressure and number of moles. And so we're looking at volume and temperature. So again, we should think about these logically. What happens to the volume of a gas if we increase the temperature? So a long time ago, one of my students learned about Charles' law the hard way. This was 1999. It was my very first semester in grad school as a TA. And I can tell you, being a TA is a very, very interesting experience because it's one of those things that I had graduated from college in May, and 3 months later, you're thrown into the classroom and told, go teach. Well, the student set up a reaction, and the reaction said it needed to be heated at a certain temperature for a period of time. And so what the student did was they set up a test tube, Well, like I said, my artwork leaves much to be desired. And then they put a thermometer in there. So everything's okay so far. But then they put an adapter to hold the thermometer in place. And once they put that adapter in place, that sealed off the test tube. And then they started heating it. Now, so some heating source down here. Well, what happens? So essentially what they did was they made a closed system and decided to start heating it. Well, what happens when you heat a closed system? Well, all this gas inside is going to build up pressure because what it wants to do is increase in size. But we've prevented it from increasing in size by making it a closed system. And so because of that, their test tube exploded. Fortunately, they were working on a small scale and there were no injuries, but they learned an important lesson that day. So if you increase the temperature, you're going to increase the volume. So these are directly proportional. And so we can say the volume of a gas is equal to some constant K times the temperature. Again, as with Boyle's law though, we have this constant that makes life a lot more difficult to work with. So we do the same thing we did before. We solve for K as V over T. And then we can say that V1 over T1 is equal to V2 over T2. And so this is the form of Charles' law that we find to be the most useful. Now what about units? Can we use any unit again? Well, for volume, yes. Just like with Boyle's law, you can use any units you want for volume. But for temperature, you must use Kelvin. Why do we have to use Kelvin? Well, remember, Kelvin is equal to degrees Celsius plus 273.15. And so the coldest temperature that can be achieved or can exist is 0 degrees Kelvin. That's known as absolute zero, where essentially all motion, all matter stops moving. So you can't go below zero. With Celsius, though, of course, you can have negative temperatures. And so you can easily imagine a situation where if you plugged a negative value in here for T1, then that would give you a negative volume. And the idea of a negative volume isn't something that really makes a whole lot of sense. So when it comes to temperature, in any of these gas law equations, it's going to be the same thing for the next law, as well as all the rest that we use and learn. We have to be in Kelvin. The third of this group is known as the Gay-Lussac law. Now we have constant volume and number of moles. So here we're looking at the relationship of pressure and temperature. And so as we already talked about with our previous example, if our volume is constant and we increase the temperature of the gas, the pressure is going to go up. So these are also directly proportional. So same thing that we did before, pressure is equal to a constant times temperature, or K is equal to P over T. And then our useful form of the equation becomes P1 over T1 equals P2 over T2. Again, same comments regarding units. Your pressure can be in any unit as long as it's the same on both sides, whereas your temperature has to be in Kelvin.